And we will look at all kinds of change. We'll look at amounts of change. We'll look at rates of change. Mathematics of change. In calculus, we can find the slope of a curve. We can find, this is a little bit of a stretch to say this, instantaneous rate of change. You really can't find that, but we can get really, really close to it. You can describe how a curve changes. We can find the area between curves. It's all stuff that you can't do without calculus. Volume of crazy, weird solids. Talk about why you would do that later as well. Work done by a varying force if you're more of a physics-oriented person. What you'll find, depending on what you do later on after this class, whether you'll go into college or maybe you continue here in Valor, you will find that even though it feels like calculus is like the pinnacle, it's like the end of math, it's actually the doorway to everything else, to real-world math, about as real as it gets. And so that's what all this stuff is about. It's a pretty cool topic. So the two big questions we answer here are the tangent line problem. That's the first one. The tangent line problem, the issue there comes down to finding the slope at point P. We are going faster this. We'll really dig through this in chapters 1 and 2. Finding the equation of a tangent line. We will often approximate a tangent line. We'll do this a lot by using a blank line. So a tangent line passes through one point on a curve, right? What kind of a line passes through 2 points on a curve? Do you know this term? It's okay if you don't. Secant, have you ever heard of a secant line? Maybe it would have been like geometry that you would have seen that, possibly. I don't know. So we'll use a secant line, and we'll use a tangent line a lot within this course. And of course, if you take those 2 points and you make them get closer and closer together, you end up with this slope of the tangent line. Please don't feel like you have to have this mastered right now. This is just a very brief preview of pretty much the entire year. So I'm just giving you a quick look ahead, and then we'll go deep. So you end up, like I just said, if you make these 2 points get closer and closer together, that secant line becomes a tangent line, and that's kind of the first great question that we answer, the tangent line question. The second one is the area problem, and this is actually far older. Newton and another guy named Leibniz developed the whole how do we find the equation of a tangent line thing. But that was in the last like 250 years. The question of how do you find crazy areas like that, right? We all know how to find the area of a circle or a square or a rectangle, triangle, those kinds of things. But how on earth would you find that area, and why would you care? That is a much older problem. It actually has its roots in China in hundreds of years before Christ. So we're talking like 2,500 years old. So much older question there. And so you could use rectangles if you wanted to approximate this area. But of course, you can see that that's going to create issues with accuracy, right? It's going to be too high or too low. What could I do with those rectangles if I wanted to increase the accuracy? Make them skinnier. And if I make them skinnier, what happens to the number of them? More of them, right? So if you had more of them and they got skinnier, and even more and they got skinnier, and more and got skinnier, what number would we be shooting for as far as the number of rectangles we'd want to fit in there? 1 million? 1 billion? How about, what if the number of them approached infinity? Wouldn't they be really, really skinny? And maybe that would actually give us the true area? It's another one of the great questions we'll look at this year. Okay? So, what connects it all? Finding the equation of a tangent line, finding the area under a curve, both involve limits. They both involve limits. And so that's where we're going to start. Hopefully this looks really familiar to you. And by the way, the summer assignment, if you need to clean it up a little bit this week, that's cool. Let's just have that due on Friday, your summer packet. My point is, some of this is going to look pretty familiar. We're going over it again because I want to make sure you're really, really good with limits. So the notation for a limit is something like this. Lim x arrow c of some function. So it's got to have all three of those elements. It's got to have lim, which of course stands for limit. It's got to have a variable like x or t or y or theta or whatever it happens to be, approaching some number. And then it's got to have what we're finding the limit of, some function, right? In this case, it's g of x. Okay? So the way that you read this, you could read it two different ways. Anybody want to venture a thought? How would you read that? Go ahead, Bailey.
You could just say the limit of g of x as x approaches c.
That's definitely one way you could say it, or you could say it a little bit differently. What do you want to try? The other way? She said limit of g of x as x approaches c. Or you could say, there you go, Eden. That's perfect. That makes sense? Doesn't really matter. You can say it either way. So then, what is a limit? So this is the thing. This is kind of the first kind of wall we hit. You guys in pre-calc did limits, right? Mm-hmm. Quite a bit. And so, you're like good at plugging stuff in and factoring and canceling and all this stuff. And then I ask you this question. Great, you can do it. What is it? And that's sometimes where it's like, I'm not so sure anymore, like what I'm doing. Like, what is it finding? What is it all about? Does anybody have a sense of that? Like what a limit actually is? Anna?
Is the y value that a function is approaching as it approaches a certain value.
Okay, I like that. Yeah. So she used some really good wording. She said approaching, right? So it's as you get closer and closer and closer. I like that wording for sure. I use this word a lot. I'm going to say it's the behavior or the behavior pattern of the y's. It's the behavior pattern of the y's as x gets closer and closer to some number. Usually we call it c. Could be whatever, some number. So the pattern behavior of the y's as x gets really, really close to c. So it's not when x is c, y is that. That's not what we're talking about. We're talking about as you get closer and closer and closer. So if I'm standing here and I start to walk and I'm headed this direction, and I said, all right, well, what's the limit of my motion? And you're not sure yet. I keep walking. All right, what's the limit of like my motion? What would you start to say? The doorway. And like, I'm not there yet, but isn't this the pattern of my behavior? Wouldn't it be really unreasonable if I asked that question, you said, your desk. Like, well, I'm walking this direction. Desk makes no sense, right? This is the pattern of behavior. Do I actually have to stand in the doorway for my pattern of behavior to be the doorway? I don't. But if I'm heading there, like I'm getting closer and closer, right? My limit is, you probably could say the doorway, right? I'm still not there yet, but the pattern of behavior is certainly the doorway now, right? I'm getting really, really close. I'm not actually there yet, but you could say that the pattern of behavior is the doorway. That's what we're talking about. You okay with that? Okay, cool. So there's several different ways that you can evaluate limits. You could use a table, you can use a graph, or you can use some algebra. Okay, so we're going to look at those, and we'll do as many as we can here. We've got about 5 minutes left, and we'll just see how it goes. So if you guys would, let's take a look here at this table. Feel free to use your calculator for this to fill out this table, A here. Limit as x approaches 0 of x over the square root of x plus 1 minus 1. Feel free to use that calculator to get those output values. And once you have those, just let me know. I will often rely on you guys for calculations like this, just so we're all kind of rolling together here. I definitely don't have these memorized. In fact, it's been exactly 12 months probably since I've done this one. So.
Mine died.
No.
Can I use my phone?
Can you use what?
My phone?
Sure. Yeah. And those chargeable ones always die at the wrong time, don't they? One of them is super easy. Of course, when x is 0, y is d and e. But all those decimals are not so cut and dried. Anybody have one I can put up there? Anybody have what do you got, Audrey?
I have 1.948 for the first one.
1.948. Let's go with the 3 decimal thing. Believe it or not, the 3 decimals is the standard sig figs for the College Board and the AP test. And also, believe it or not, if you don't include 3 decimals on a decimal answer like this, you could lose points. So we will practice that throughout the year. Anybody have that negative 0.01? Anna, what do you got? 1.994. Anybody have the negative point or negative 0.001? Bailey? 3 nines? Okay. Anybody have any of the positives? The 0.001?
That wasn't.
2 point, okay, yeah. 2.3 zeros and a 5. Okay. Starting to see the pattern take shape here? Can you see the doorway to go along with my analogy? How about that 0.01? Heather, right? What is it?
2.05.
Oh, just kind of like the other one. Okay. And anybody have 0.1? 2.049. Okay. So we can't say for sure here, but looking at the pattern of behavior of the y values, what would you have to guess that the limit is?
2.
It's 2. Yeah. Totally agree with you there. Okay. It's just using a table. I think that's a valuable thing. Although you got to admit it's kind of slow, kind of gangly process making this whole table and looking for the pattern. And it's really not that reliable either because you can't say for sure. Because anybody say absolutely that it's not 2.27 zeros and a 1? You really can't say that for certain, right? We're just assuming that we didn't get some crazy number like that. But I think 2 is right. Okay, so then a graph, this will be the last one we do today. A graph would be the other way you could do this. And so I've got 3 questions to go along with this graph. So this will be helpful to have the notes in front of you here. What do you guys think about the limit as x approaches 1? What would you say that is? Just looking at the graph. Pattern of behavior of the y's. 1. I totally agree, yeah. Can you see how, as we approach from both directions here, the y values look like they're approaching a 1? Okay. So then what would you guys say about the limit as x approaches -3? 1, 2, 3. Say again? 2. I think, yeah, 2 seems very reasonable there. Again, we're looking at a graph, and couldn't somebody argue that, no, I think it's 1.999999? Of course you could, but we're always going to assume integer values when we're looking at graphs. So 2, and again, we're looking at this and just saying, as we approach -3 from both directions, it looks like the pattern of the y's is 2. Okay, and then the last one for today would be that last one. This is a contrast, right? So at the start, we did the limit as x approaches 1 of g of x. And now this last one, I'm asking you to find g of 1. So what's g of 1? Does not exist. Why? There's a hole. Exactly right. So g of 1 simply doesn't exist because the graph does not exist there. There's some issue, and now the graph just does not exist there. But the limit does, right? Because the limit is more concerned with the pattern of behavior of the y's versus what's actually happening right there. Make sense? Okay, so we obviously have just a little bit more to go with section 1.2. Is it just one example? I don't know. It's not very much. We'll clean that up tomorrow. 1.3 intro video is due tomorrow. If you have any technical issues or something like that, please let me know. So that means don't try to do it at 1 a.m. because I'll be sleeping, hopefully. Anyways, it's nice to meet you guys. I'll get to know you much better as the year goes on. Hope the rest of your day is good. That assembly is next. And you guys know, is it in the gym? It's got to be in the gym, right?